exercise physiology application video number 5. So today was a pull day, so back and biceps, and so again, things we're talking about, we're going to be talking about predominantly higher intensity weightlifting, if you haven't noticed a trend here. So in class we've been talking about the nervous system and how that ties into our movements, and in particular muscular contraction. And so in my last video I got into the actual process of what's happening in the axon when we're dealing with depolarization, repolarization, that refractory period, and what's happening in terms of the movement in and out of the cell. So just as a quick refresh, in depolarization we have sodium flooding into the cell. Once we get an action potential, those sodium gates shuts, then potassium gates open, efflux of potassium, then we have to reestablish our resting membrane potential during the refractory period. So our sodium potassium pump, which requires ATP, which we're generating from our bioenergetics, the glycolysis, Krebs, etc. But it fuels that sodium potassium pump, which allows us to reset our resting membrane potential. But the speed that membrane potential reaches that threshold is different depending on the type of exercise and the different energy pathway you're using. So for today, when I was doing weightlifting, I'm lifting heavy weights. We'll say I'm doing a set of 5 reps. I need energy very fast. So I'm using my PCR, predominantly really just PCR. I guess you could say I'm getting into a touch of fast glycolysis, which that converts to type 2 fibers, your fast twitch fibers. And they're called fast twitch because you have to quickly get that ATP. And when you do that, you're using, you have your motor units, which is your neuron, and it's all the muscle fibers you're innervating. So it's your axon terminal can innervate one muscle fiber, but since your axon can have so many of those terminals, you're able to innervate multiple muscle fibers. And so when I'm doing large movements like a pull-up, I'm having to innervate lots and lots of those motor units because it's a forceful movement. And if you look at Henneman's that graph, the ratio, as I'm using more and more force, I'm recruiting more and more motor units. So let's say what happens when I'm trying to do those pull-ups, or say a deadlift, that might be easier in this example, and my body just quits. I'm trying to do my 1 max for deadlift and I can't do it. It's my proprioceptors. So in my muscles, my tendons, my Golgi body organs, they measure the tension of my muscle. And so once it reaches a certain point, when I'm trying to accelerate and recruit so many motor units too quickly for my body, when I'm doing that to a point where that acceleration of tension may actually cause injury, my Golgi body tendons say nope, and they stop it. And they do that by sending inhibitory postsynaptic potentials down my axon, which is the same idea that we talked about with the potassium, the sodium, but you can either have excitatory postsynaptic potentials or inhibitory. So when you're getting ready to do the movement, it's excitatory. You're getting your muscles ready to go. But when your Golgi tendon organs are saying, hey, this is too much tension, the body's going to get hurt, you start to release inhibitory postsynaptic potentials into that synaptic cleft, which shut your muscle off and prevent any further movement from happening. If I were to have done more endurance-based exercise today, I would be using fewer motor neurons because I'm wanting sustained energy, things that I don't need huge forceful movements for. So let's say I'm running, my hamstring is contracting thousands upon thousands of time. I'm using my smaller motor units. But doing things like a deadlift for sets of 5, I need my big motor units, and I need them quickly. So I'm in, again, PCR, fast glycolysis, type 2 fibers, and I'm going pretty quickly and pretty high up on Henneman's size graph. And yeah.